welcome back to Smart Geometry. Today we're talking about segment relationships. Let's kind of start with some basics. Again, this is a nice little ruler right here. This right here is a segment. Again, if we forgot what a segment was, it is a set part of a line that has two endpoints, a beginning and an end. Okay, now this ruler postulate, just a very, what you call common sense question is that, hey, wherever I start on my ruler, that is not considered the zero that we go on from there. So even if we move this here, let's say we started at 1, really this not becomes the new 0 and we measure it that way, so we get the proper measurement. Okay. Now, let's talk about the segment addition postulate. And this, my friends, is very important because we will use this a lot. Not just this chapter, but next chapter, and anytime we really deal with segments. And also, just kind of like when we're doing some finding distance stuff, we did this without actually talking about it. So in any segment where there's 3 points, in this case we're doing A, B, and C, excuse me, and B is some point in between the two endpoints, B has to, the sum of those two individual segments is equal to the distance of the whole thing. We kind of done that before. I think a problem in your on your test was saying, hey, the whole thing is 30. One segment is 17. What's the other one? It was very easy to do. I mean, we just subtracted those and got 13. And that is true. But generally speaking, understand that anytime there's 3 collinear points and there's 1 point in between, endpoint to that point, and then that point to the other endpoint, those 2 segments, this segment and this, equal the whole thing. We have a hard time doing that sometimes. We have a hard time picturing that in our heads. When we just saw numbers, either added them or divided them or subtracted them. So some of us just subtracted them and like, oh, we just happen to get the right answer because I just happened to ask the right question. But understand, any big segment, if there is a point between, can be divided into 2 smaller parts, and 2 smaller parts can be combined to make a big part. This is the key to most of this section's homework. So let's go over other parts. You've seen this before, properties of congruency. When 2 parts are the same, they're called reflective properties. We usually say this before we subtract or add anything. Symmetry is saying when you say forwards or backwards, it's still the same thing because they're symmetric. They are the same forwards or backwards. And transitive property is when you say when there is a common part that combines 2 different things, you say that the first thing is equal to the last thing. Now again, this definition of congruency is what we're going to use to say, hey, things that are congruent are also equal. Things that are equal is also congruent. This is a biconditional statement. It works both ways. So that being said, let's kind of go to an example that'll be on your homework, very similar to it. So the given again is always the statement that is 100% true. The prove is the thing we're trying to ultimately show is true. So I'm going to hide this for a second so we can see this. There we go. So given, let's look at the information. It tells us that C, segment CE, and FE are congruent. So we're going to mark them as congruent. They're going to mark them the same statement. Those 2 are congruent. And then ED is congruent to EG, so they'll have the same mark, a double mark and a double mark. So a single mark is congruent to a single mark, and a double mark is congruent to a double mark, okay? That is true. We want to ultimately say that the whole segment is congruent to the whole segment. So if we were just using numbers, this will make a lot more sense, but we aren't using numbers. But let's say, just it seems kind of common sense. Let's say this right here is 4, and this right here is 6. Well, because these 2 are the same, this is also 4 and this is also 6. So we can prove that 4 plus 6 is equal to 4 plus 6. That's the goal we're trying to do here, but without using just numbers. We're trying to generalize this by proving it without numbers, which makes it true for all possible examples, just like this. That's what a proof does. It proves it for all possible examples. So we always start with the given statement. We'll start with that. CE, segment CE is congruent to FE, and you can put them both on the same line. Colon, ED is congruent, wave, there you go, EG. Okay, that is given information. Now, like we said earlier, we're switching that We're saying that CE is congruent to FE. This should have lines over them. We're not saying CE is equal to FG. As we said earlier, anytime you said something that is congruent is now equal, all you're doing is to make it parts that are malleable, parts that we can move. When they're congruent, you really can't move them around, but when they're equal, we can move them around a lot more. So this is definition of congruency. You can just put definition of con. That's an I will understand that's definition of congruency. So here we're saying that CE, this segment, plus ED equals CD. We just talked about this earlier. When you combine two smaller parts, two smaller segments to make the whole segment, knowing that those points are collinears, that's called definition of congruent. No, sorry, it's not definition of congruent. My bad. It's segment addition. We're adding segments. These are individual segments being added to make a bigger segment, so that's segment addition. Postulant. Segment addition. Okay. As we said earlier right here, anytime you're adding two smaller parts to make a bigger part, to make the whole thing, that's segment addition postulate. Here, postulate. Shorthand be, or you can write seg add post. Same thing, seg add post. Now let's look at this. We went from saying this to saying this. What happened from here to here and here to here? What's the relationship of CE and FE? Well, we always look at the above stuff. This is the only stuff that we can take as true. We look above, we say, hey, well, at one point we said that CE is equal to FE. So if we know these are equal, when you replace it, what is the mathematical property we are doing? We're doing substitution. Substitution property. That's what we did. We substituted. Now, they're telling us in the, step 5, we're doing another segment addition postulate. So what other segment can we add? Well, we added this one already. So the other one left is this one over here. We can say that segment FE plus segment EG equals the whole thing FG. We're allowed to do that because they are collinear and they form the entire segment. So that's segment addition postulate. So let's look at this information. We know that above FE plus EG equals CD and FE plus EG equals FG. Our goal is ultimately to say CD on one side and FG on this side. So on number 5, as of right now, we kind of have that going on. On one side, we have FG, and they're telling us we're going to do some sort of substitution. Well, what can go into this spot right here? Like we said earlier, earlier we said that CD equals FE plus GE, so we can put that in there right there and say CD is equal to FG. We substituted that information because above we said that those two parts equal this, but they also happen to equal something else, so we substituted. It's also sort of a form of transitive property. The only reason we didn't say transitive property is because it was not said properly above. If above we would have said, hey, CD equals FE plus EG and EG and FE plus EG equals CD, then we had those two parts properly in the middle, quote unquote. So then we can say the first thing equals the last thing. But this is another way of doing that. Transitive property and substitution are very similar and they can almost be used the same, but there's just some technicalities there. And now all we did is say, instead of saying CD equals FG, to saying CD is congruent to FG. That again, similar to switching it from congruent to equal, we can switch it from equal to congruent by definition of congruency. And that's it, y'all. That's what the majority of today's assignment is going to be. It's just working these proofs with these particular statements. You'll use this a lot, you use this a lot, and you'll probably use this a lot. These 3 statements will probably be the main reasons why we say the statements that we do. So these are our statements. I don't know if we did that last time. Our statement, and these are our reasons why we say those statements. Reasons. Those are very important. If you need any help, feel free to ask me. Thanks, y'all. Bye.